Welcome to Data Analysis Made Easy with Microsoft Power Tools number 6. And in this video, we got to cover the fundamentals of DAX. That's the functional language in the data model in both Excel, Power Pivot, and Power BI. Now, here's the funny thing. This video is the same as video number 17 in the MEX series. However, I added a new section to the end about an amazing query option in Power BI. You are not going to believe all the amazing topics we have in this video. And we'll see, yes indeed, 66 different DAX formulas. We'll cover calculated columns in row context, measures and filter context, the SUMX function, the calculate function to change the filter context, time intelligence functions, the ever important override operation, functions like KEEPFILTERS, and perhaps the most important topic in DAX, context transition, table filters, grain, cardinality, and much more. Now, this is the fourth video where we talk about the calculation power of Microsoft Power Tools. We saw that sometimes pivot tables were perfect, sometimes formulas were perfect. M code, of course, is perfect for what it does, but sometimes in the data model, you got to use DAX to handle that big data. Now, each one of the tools has their strengths, but in this video, it's all about DAX. Now, one of the main ways that Excel worksheet formulas distinguish themselves from M code and DAX is we can point anywhere in the worksheet. We can point to a range of values. We can point to cell references. And when we copy our formula, we can see exactly where the formula is pointing. Now, what Power Query M code functions do so well is we can actually deal with data. We can point to actual files. Here we have a column of tables, and different than over in DAX, we can still see what we're dealing with. There's a table, and I'm allowed to use a function to combine those tables. Now, when we jump over to DAX, there are two amazing things that DAX does better than M code or worksheet formulas. Now, this is a formula to calculate average monthly sales using DAX. This is Power BI Desktop. This is over in Excel Power Pivot. Now, the two things that make DAX so amazing are both virtually invisible. Now, the first is DAX can deal with big data. We use Power Query to load this to the data model. But in that data model, there's a special thing called a Columnar Database, which compresses the data and makes DAX formulas like this work efficiently over big data. Now, we actually can't go and look at this Columnar Database, which means it's invisible, but we can get previews of the data both in Power Pivot and Power BI Desktop. The other thing that DAX can do is it can take a calculation like, for right here, I just want average monthly sales for Aspen. Now, if we used other features, we'd have lots of intermediate steps. And notice, we had to calculate a whole table of monthly sales before we calculated the average. But with DAX, we can do all of that in a single formula. Now, DAX allows us to work with tables and columns at different grains. That just means different sizes, like a monthly total, much more easily than the other formula languages. Now, this values function is the part of this DAX formula that's creating a table inside the formula. It's actually creating this table. That means with a single formula element, we have real power. But that's the invisible part. We can't see that this is a table like in worksheet formulas where the formula is pointing to a range of cells. Now, even though it's invisible, in this video we'll try to understand parts of the formulas like this so they don't seem so daunting because it brings real power. So big data, complex calculations done with a simple formula, bam, that's DAX. Now, since DAX and the Columnar Database are really invisible, Throughout the video, I'll try to visualize things like what this table is actually doing and other things like filter context and row context. As is always the case, I have an Excel file. This is the start file where you can practice what you see. Here's the Power BI desktop file. But before you start, you have to use data source settings. And this is one of the folders you have to download. You have to click Change Source and point your computer to this folder on your computer. Now, you can work in either the Power BI desktop or Excel file. The DAX is almost identical in both. There are some differences, and I'll point those out. There's also a finished file in Power BI Desktop with all of the DAX formulas. Same thing in Excel. There's a finished file. And there's a bunch of other files, too, with examples we'll use throughout the video. And don't forget the PDF notes. 50 pages of amazing notes with lots of cool graphics like how filter context works, how row and filter context work together, pictures of the formulas themselves, and lots of other diagrams and written content. Now, we'll start in the PDF notes and ask the question, what is DAX? Well, DAX stands for Data Analysis Expressions, and expressions just as a synonym for formula. Now, DAX formulas are created in the data model in either Excel Power Pivot or Power BI. DAX formulas are programmed to work efficiently with big data and can significantly reduce the number of intermediate steps in complex calculations by creating columns and tables within the formulas at the correct grain or size. Now, DAX includes many functions that are almost identical to Excel worksheet functions like sum, average, and end of month, but it also has amazing unique functions like related, SUMX, and calculate. Now, the four main advantages of DAX formulas are, well, measures. Those are the formulas we use in pivot tables and Power BI visuals. They are reusable, pre-formatted, metric in nature, aggregate formulas that you can drag and drop into our pivot tables and visuals. That means create, format, and then use over and over. Now, even if you only use DAX for sum, average, and counting, just the fact that we can format them with number formatting, that's a huge advantage. Think about when we use a standard pivot table. We may drag and drop the sales multiple times, but every time we have to add number formatting to each one of the pivot tables, but not with DAX. With DAX, we add number formatting directly to the formula. Now, of course, as we mentioned before, DAX formulas are specifically designed to work with compressed data from the data model and will calculate more quickly over big data than most other tools. Now, there are many more functions available in DAX than there are in a standard pivot table, but not than the functions available in the Excel worksheet. Now, perhaps the most beautiful and amazing thing about DAX is it makes it easy and efficient to use tables with different granularities within the formula. And this definitely can reduce the number of intermediate steps in complex calculations. Now, next, we want to talk about the components of the data model, because how each works in relation to DAX is important for our understanding of DAX formulas. Well, of course, we have the in-RAM columnar database. We have relationships between related tables, different types of DAX formulas, calculated columns, measures, and tables. And hidden columns and tables, they're important for the reporting visualization side, but they're also important because they can help prevent an unwanted implicit DAX measure. All right, now I want to jump over to our Excel file. Now, first things first, when you import data, use Power Query. This is Excel. In Excel, do not use that button right there. Power Query gives us much more control over the data and correctly configuring and formatting and adding data types to the data. In Power BI Desktop, you don't have a choice. There's only Power Query to import data. Now, here's our data set. We have a sales table with 2 million rows, and then product, sales rep, and date. And when we imported this, we sent this to the data model. But here's what the Columnar Database does. And this is a simple example. We have an original table with 606 records. If we take 606 records times 4 columns, we get 2,424 little bits of data. But when the Columnar database gets a table, it stores each column individually as a unique list. Now it builds a sort of map that it uses to reconstruct the data when we do analytics with our measures. By storing individual columns as unique lists, it makes the data stored in the in-RAM database much smaller. So that means for this table, instead of 2,424 bits of data, we only have 621. There are also calculations that happen in the engine with the Columnar database. And one of the calculations in particular, distinct count, well, the reason that the formula works so fast is because the Columnar database already knows what the count is for the unique lists. Now, if we look at our data model, we're going to look at diagram view. In Power BI Desktop, it's model view. Now, before we can create DAX formulas, we have to understand the components and structure of a data model. Now, this is called a star schema data model because it has a fact table in the middle, and fact tables have foreign keys like product ID and supplier ID, and then columns that we want to make calculations across. Surrounding the fact table are lookup or dimension tables. These have a unique list with a primary key. Now, for each primary key, product, sales rep, we have attribute columns like category, supplier, and region. Those are the columns we use in the reporting area as conditions or criteria for our calculations. We also have attribute fields like price, where over in the fact table, we can use a lookup formula to go and get the price, bring it back, and use it in a formula. Next, we have relationships. Primary key, foreign key, that means one of each, and duplicates. That's why we use a one-to-many relationship. Now, this relationship does two things. It helps us do lookups on this side, the fact table or many side. And when we drag and drop our fields from dimension tables into visuals and reports, that creates a filter so the calculation knows which criteria to use to make the calculation. And that condition or criteria or filter flows across the one-to-many relationship from the dimension table over to the fact table. That causes the fact table to be filtered down to a much smaller size. And that's one of the main ways that the data model and DAX formulas are allowed to calculate quickly over big data. The other important component is we've hidden fields. Sometimes we hide tables. This field right here is hidden, so when we're over in the reporting area, we don't use it because we're never going to need it. But over in the fact table, we want to hide all of our fields. In particular, fields like units sold and cost of goods sold, we don't ever want to accidentally drag and drop those into visuals because they create implicit measures which cause a lot of trouble. Now, this is a star schema data model, and when we can, we want to create this type of data model because it will help us build efficient DAX formulas. Now, we do get other types of data models, like a snowflake data model with lots of dimension tables. We might get other types of relationships or even multiple fact tables. But when we can, we create this kind of structure, and things will go more efficiently. Now, of course, the final component of our data model are DAX formulas. Now, let's go over to Data View, and we'll select F Sales. And there are two main types of formulas besides DAX table formulas, which we'll talk about later. But the two main types are calculated columns. This would be like line sales for each transaction in the fact table. A calculated column formula would be similar to an Excel table calculated column or a Power Query custom column. The second type of formula is called a measure. Down here, this is the measure grid. And in Excel Power Pivot, we create our measures here. Measures are the pre-formatted, reusable aggregate formulas that we drag and drop into visuals. So we'll create a calculated column for line sales, and then a measure to add those sales. Over in Power BI Desktop, we go to Data View, select our table. This is where we create our calculated column using the New Column button. And when we want to measure, we select the table, There is no measure grid like over in Excel, but we select the table and click New Measure. Now let's start by talking about calculated columns. When we create a calculated columns in a data model, we have three scenarios. One is we want to calculate line by line sales in the fact table, so we're calculating amount that will aggregate later. The second use for calculated columns is in a dimension table. We might add an attribute column that we're going to use in the pivot tables or visuals for conditions or criteria. So we might add fiscal year, end of year, or other date attributes in this dimension table. And the third type of calculated column is a column where we want to replace a very complicated measure, so we do an intermediate step that helps the eventual measure to be much less complicated. Now we'll see examples of all three calculated columns. Now let's start off over here in Excel Power Pivot. Here's the calculated column, and we double click the add column and then type the new name of the column, call it line sales, and enter. Now we go up to the formula bar where we create our formula. And for us, we want units sold times, and we're going to have to look up in the D product table the retail price. Now I'm going to do that first. We don't have XLOOKUP over here. We have a function called related. Now remember, relationships help us on the fact table side to look up things from the dimension table side. So that's why it's called related. And the amazing thing about this lookup function is because there's a relationship, all you have to do is give it the name of the column of the item you want to look up. So I'm going to double click retail price, close parentheses. Now before I finish this, I'm going to hit enter, enter. See, it looked up the price for product 1, product 2, product 3, and so on. Now we can complete our formula. We click back in the formula bar, times, and we need to get the column reference for units sold. Now over in Power BI Desktop, we actually type out the column reference, but over here in Power Pivot, it's similar to an Excel table. When I see that downward pointing arrow, I can click. Now it puts the correct syntax in for a column reference. Full table name, and in square brackets the field name. And it's the same in related. The correct table name, and then in square brackets the field name. So now when I hit enter, the formula calculates the correct transactional line item sales for every row. Now this is a DAX calculated column. And just like Excel table formulas in the worksheet or Power Query custom columns, that formula is the same in every cell. Not only that, but we have to use full column references. We're not allowed to use cell references like in Excel worksheet formulas. So how does the formula make its calculation? It uses something called row context. And all that means is that for any particular cell in this calculated column, you can see all the values in the row. So related for this amount right here is looking up product price number 1, and it's using units right there, 7, to make its calculation. So for every calculated column that you create, row context is created automatically. Not only that, but in DAX there are DAX Iterator functions like SUMX and filter. They both use tables and make calculations for each row in the table. So calculated columns generate automatic row context for every row in a table, but so do iterator functions. That row context is created inside the formula. Now, another thing about row context that's different than all of the other formulas we used, notice we used a full column reference. So in a DAX calculated column, we use row context to get the values in each row. If we're using worksheet formulas, we'd use cell references to see the values in each row. If we're using an Excel table, we use the implicit intersection operator, that @ symbol. And if we're in a Power Query custom column, we have to use the each keyword with the full column reference. Now, the next important thing about calculated columns is when you create all of these values, they are stored in the Columnar Database. This becomes a new unique column in the NRAM Columnar Database. that increases the size of the database in the RAM. As we'll see later, though, X Iterator functions sometimes allow us to substitute for a calculated column, and then we don't have to store the values in the in-RAM Columnar Database. Now, because we created this calculated column with DAX formulas and it's stored in the Columnar Database, we didn't get the opportunity to use Power Query to assign a data type. But automatically it got assigned the correct data type, decimal number. Now, before we create our measure to add all these, let's go create our second calculated column. Let's go to D date, and we want to add an attribute column here. So I'm going to double click add column. We're going to call this end of month, enter. And just like in the Excel worksheet, we have in DAX end of month. I'm going to select the date column. It'll see every date using row context, comma, and I want the end of the current month. So we put 0, close parentheses. And when I hit enter, row context allows the column to calculate the end of the month for every single row. Now, this field could be used in reports if you want to see the end of the month, but it also will be helpful when we calculate monthly sales. This, in essence, will be a helper column that will allow us to calculate monthly sales. Now, we'll see the third example of calculated columns later. When we have a complex measure, we'll come over and add a helper column inside the date table. Now, let's go back to F sales. Now, we selected F sales, and we're going to create our first measure here. The measure that we create in this measure grid below the F sales table, that measure will show up in the PivotTable field list or over in the visualization area in Power BI desktop under the F sales table. Now our goal is to add the line sales. We come down, and usually I select a column and widen it so that I can see what we're going to put for each measure, the name, assignment operator, and the formula, and the number formatting that we apply. All right, so we click in a particular cell, and we first type the name of the measure. I'm going to call it two-step total sales because first we create a calculated column, and second we're going to create a measure. Now the assignment operator, that's what separates the name of the measure and the formula. In Excel Power Pivot, we use : equal sign. Interestingly enough, that's the same as we do over in Access if we're building formulas. But over in Power BI Desktop, we just use an equal sign. Now we type sum. Now we can select the column, close parentheses, and enter. Now over here in the measure grid, when we create a measure, we're always going to see the grand overall total. That's the amount we'd see at the bottom of a pivot table or a Power BI visual. Now the reason is because in the measure grid, there is no filter context. We'll learn that filter context is what works in a pivot table or a Power BI visual to calculate an individual amount given the conditions and criteria. Now let's add some number formatting. Now that number formatting will show up anytime we drag and drop this measure into any report or visual. Now before we go and use this in a pivot table, I want to jump over to Power BI Desktop. Now over here in Power BI Desktop, we're going to create those same 3 DAX formulas. Now let's start in Data View or Table View, and we want to create a calculated column. So we select the table, F Sales. We're going to create the column right here, Line Sales. I select New Column, and we don't double click over here to create the field name. We type everything in the formula bar. So Line Sales equal related, down arrow. Remember, we cannot select columns over here in Power BI Desktop. Close times F sales, and we'll go down and get units sold. There's our line sales. Enter. And there are the line sales in our calculated column. We got data type decimal number. That's fine. Over in D date, we'll actually see how to create a date table over in here in Power BI Desktop with a single table formula later in this video. But oftentimes we have date tables and we want to come and add a calculated column. So we select New Column. This is the same end of month. we'll go to ddate date, comma 0, close parentheses, and enter. Now, this created data type date time, and that's not what I want, so I'll create date. We can format this also, although we're never really going to use this necessarily over in any visuals. There's our second calculated column. Now, let's create our measure. We'll go back over to F sales. And usually, since I have to come over and select the table to create the measure, I just come over and right-click, and right at the top is New Measure. You also have a button up here. So we'll select New Measure, and there's no measure grid to show us the name, formula, and number formatting. But we created up here 2-step total sales, and the assignment operator is just an equal sign. Sum F sales, and there's our calculated column. Now a column in the drop-down. Close parentheses, and enter. And we can add some number formatting. Now, generally what I do over in Report View is I create a tab with formulas. And if you want the grand overall total, you can select multi-row card, and then check your measure, and sure enough, there's the total. Another option is you can, let's create a matrix. And I'm going to select a particular attribute. I'll say products. And then as I build the formulas, I just keep adding the formula. It'll show me the grand total at the bottom and the individual amounts. So I'm going to check. So there's the initial 3 formulas in Power BI Desktop. I'm going to tend to work over in Excel, but by all means, you can work in either Power BI Desktop or Excel Power Pivot. Let's jump back over to Excel. Now, over here in Power Pivot in the Home tab, the Pivot Table dropdown actually has some great options. You can create simultaneously a pivot chart and table. You can create 4 charts at once, or even a flattened pivot table. Now, I tend not to use these, but if you need 4 charts, that's a cool option. Now, over here on the total sheet, I have B2 selected. Go up to Insert, Pivot Table dropdown. And there's an option to go directly to the data model. Now notice the underlined D, because I like to use keyboards, Alt-NVD. I'll invoke the OK button with Enter. Now here's our pivot table field list, and it is sort of annoying because we have a D date and a second D date. Yeah, this D date icon means the actual Excel table from the worksheet. The little orange cylinder, that means Query Generated Data Model Table. So if we want product, we come to the orange icon cylinder, check products. We can come down to F sales. There's the icon over here in Excel Power Pivot. That means that's a measure. When I check, there's the measure, including that number formatting. If we come over to Active, the tables that we checked, there they are. Now, here's the magic of DAX. Remember, that's a single formula, and sure enough, there's the grand total as we had over in the measure grid. But how in the world did that measure calculate the correct amount for each product? Well, the measure uses filter context. And here's what it means. Remember, there's a relationship between the product table and the fact table. So when the measure hits that cell, that condition or criteria from the row area of the pivot table or the Power BI matrix or visual, it flows into that measure, and the fact table is filtered down to just the records for Aspen, and then it makes its calculation. If we look at the data model, when that measure hits the Aspen cell, the entire product table is filtered down to just one record, Aspen. And that condition or filter flows across the relationship and filters this down to just the records for Aspen. And then the measure makes the calculation. Still another way to see filter context on page 11 in our PDF notes. When the measure hits the Aspen cell, just for a moment, the fact table still has 2 million rows, and the dimension table still has 16 rows, 1 row for each product. But as soon as the measure sees Aspen, the entire product table is filtered down to one record, Aspen. across the relationship that filter flows from the one to many side. Then we end up with 110,000 rows for Aspen records, and over here 1. So that measure, instead of calculating over 2 million rows, is calculating over 110,000 rows. Now filter context gets even better. If we come back to all, open sales rep, I'm going to drag region down to columns. Now we have conditions across the column. We come up to PivotTable Analyze, insert a slicer, all. We want year, OK. Now when I select 2017 for any intersecting cell, now the measure has multiple conditions flowing in, creating a final filter context. From the product table, kangaroo flows in. From sales rep, SE flows in. And from the date table, 2017 flows in. Now before we look at the actual data model, remember 2017 is selected on that slicer. But there's many rows over here because, of course, there are many dates in 2017. So when we go over and look here, the single product is flowing over filtering, single sales rep going over across a relationship and filtering, and then every single date for the year 2007 flows across a relationship, and that fact table is only filtered down to all the conditions. Then the formula makes the calculation. So the external filter context can be defined as whatever conditions are coming from the row, column, or filters. Now the next DAX measure that we want to create is not total sales. I just want to count how many transactions for product kangaroo in Southeast in the year 2017. And we're going to use perhaps one of the most spectacular functions in DAX. It's called COUNTROWS. This is like a supercharged COUNTIFS function. Not only that, but COUNTROWS will give us an indirect way to look at the fact table. Because right here, if that fact table is actually filtered down to just the transactions for the external filter context, if somehow we could count how many rows are in the fact table in that cell, it would give us an indirect way to see that filtered fact table, and it tells us how many transactions there were. Now on page 36 in our PDF notes, this is called the expanded table diagram. And we have field names, table, field names, table. And for any given field in this list here, if we pick year, we can look across, and any column that has a color tells us that table will be filtered. So of course DDate will be filtered, but also FSales. This table also lets us know visually that the fact table really contains all columns in the data model. That's why no matter what column we use to filter in the data model, it'll show up in FSales. So when FSales is inside of COUNTROWS, we get the correct count for any set of conditions. So in the measure grid, we're going to name this count transactions, because COUNTROWS on the fact table will count whatever it is that each record in that fact table represents. Count transactions and then count rows. We put the fact table in. Notice all we need is a table. Tab, close parentheses, and enter. We'll add some number formatting. This is a count, so we decrease the decimals. And sure enough, that's how many rows there are in the fact table without any filter context. That's how many transactions there were. And guess what? It matches the number down here in the Power Pivot window. Now let's uncheck total sales, check count transactions, and look at that. There are 4,104 transactions for kangaroo SE in 2017. Now, what makes COUNTROWS so spectacular, the supercharged COUNTIFS function, is we can create any type of pivot table. Let's create a new pivot table. Let's drag year down to row, and then our COUNTROWS function down to values, and instantly we get a count of all the transactions by year. So it doesn't matter what condition we use, COUNTROWS will just tell us how many transactions. Now for our next measure, I'm going to drag region off of column, drag total sales down above count rows. We have our two measures. Next, we want to see an alternative for this total sales. And we'll look at two alternatives. One's going to be a bad option, the other one a good option. Now, if we look over to F sales, we mistakenly left a raw data field in our field list. We were supposed to hide it to prevent implicit measures. Now, to see the trouble that an implicit measure can create, let's drag and drop this raw data field down into values. And sure enough, it did sum the sales, but there's a bunch of problems. Now, over here, we can see a few problems. There's no automatic number formatting. It doesn't appear in the field list, so we can reuse and drag and drop. If we go over to the data model, now when we created that implicit measure, when we look in the measure grid, it should show up. But unfortunately, Advanced, by default, Show Implicit Measure button is not selected. So anytime you create a model, you should select this button. Then, if you create an implicit measure, there will be a visual cue. Now I'm going to cut this and paste it in our list. And if we look up to the formula bar, we can see a bunch of problems. It is read-only. We're not allowed to change the name. We can't change the formula. We're not allowed to add number formatting. In fact, if you look over here, it's all grayed out. And another problem is if you create many implicit measures and start changing the aggregate calculations, you'll create all sorts of unnecessary, unwanted measures. Another thing, it used to be that when we uploaded a data model like this to Power BI Online, which was a great way to share your model or your reports, these implicit measures wouldn't show up. But apparently, Microsoft changed that recently. Let's go back to our pivot table. I'm going to leave it there as a trail. I sure don't want to use these because just the number formatting thing alone is such a breeze. Now, our second option for total sales is the one-step method. Two-step method means create a calculated column, store in RAM, and then do whatever calculation you want using that column. Well, we can do both steps in a single formula. Now, think about what we did here. We iterated each row in the F sales table. Well, there's a function called SUMX. And all we have to do is say SUMX, use the F sales table, and we literally can copy and paste this into the formula. And SUMX will simulate this entire calculated column in the formula and then add. We're going to call this total sales one step, and we're going to use the amazing SUMX function. There's only two arguments. First argument, table. That's the table that we would have created the calculated column in. So F sales, comma, expression. We just put the exact same formula that we would have put in the calculated column. And we'll multiply that lookup function related times F sales unit sold. Close parentheses and enter. We'll add our number formatting. And with our one-step method, we get exactly the same answer as the two-step method. Now, we don't need this column at all. Right-click, delete. Yes. And it's working like a charm without that calculated column. Now, I went ahead and undid that so we can leave a trail. Now the question becomes, when do we use one-step and when do we use two-step? Well, let's think about the characteristics of each. When we have a calculated column, it gets stored in RAM. And it's calculated when we create it or when we refresh the data set. For a one-step measure, every single one of the values has to be created when you drag and drop this into a report or visual, or when you change the condition or criteria. And the values are not stored in the in-RAM Columnar Database. Now, the convention is to not do the two-step and just use the one-step method. But there could be a performance difference, because if you're dragging and dropping this into a visual and it starts to calculate slowly, then you might want to choose the two-step method instead. Now, as the great DAX masters, Marco Russo and Alberto Ferrari say, until you get to about 100 million rows, it's up to preference. So you can use either one you want. Now, we used SUMX here, but there are other X iterator functions like AVERAGEX, MINX, MAXX, CONCATENATEX, and others. And we'll see some of them later in this video. And they all do the same amazing thing. They all have a table in the first argument, a formula in the second argument, and they take that formula. And because it's a table and we're iterating, the formula has row context. So when related hits row number 1, it can see whatever the product ID is to look up the price, and it sees the units. So SUMX takes the formula, iterates down every single row, calculates the intermediate amounts, just like over here, but inside the formula, and then the sum part adds. Now, I changed this to match two-step up here, and if we go over to our pivot table and drag one step total sales, well, we get exactly the same thing. But there's two amazing things happening simultaneously with that measure. So for Aspen, we get the same amount, but guess what? Filter context out here allows the Aspen to flow in, and then once that gets to the fact table is filtered down to just the Aspen records, and then row context takes over to calculate the amount for Aspen in every single row in the F sales, calculate the intermediate values, and then sum to get the final result. Now here's page 16 in our PDF notes. Here's our formula, and in the Aspen cell, well, filter context allows from the product table the Aspen to flow in and filter the F sales table. That means that F sales is not all records. It's just the Aspen records, product ID number 5. Once filter context filters the table, then row context takes over. This formula in the second argument, well, it goes down every single row for product ID 5, that's Aspen, calculates the intermediate amounts, and then the sum in SUMX adds all the numbers to get the final result. Now this result, of course, doesn't have a filter, but if I unfilter, bam, there it is. Filter context and row context working together in a pivot table or visual and inside SUMX. Now I'm going to leave all of these as a trail. I repeated the formula with a name that I want to use over in the reporting area. Now we want to calculate total cost of goods sold, and we already have as raw data the line item amounts. So we'll call it total cost of goods sold. We're simply going to sum, close parentheses, and enter. I'll select both, add comma, and now we want to see how to use measures not over in the reporting or visualization area, but use measures in other measures. Now, a common metric in retailing and manufacturing is called gross profit. It's total sales minus the cost of goods sold. Gross profit, colon, equal sign. And the convention for measures is we type a square bracket. You do not need the table name in front of the square bracket. Table and square brackets, that's the syntax for columns. So we type a square bracket, and look at that. Available measures show up. We want total sales, and from total sales we want to subtract. Now over in Power BI Desktop, you have to type it all out, but over here in Power Pivot Measure Grid, I can just click, just like a cell reference, and it puts the measure in. When I hit enter, there's the grand total with no filter context for gross profit. Now the next measure we want is gross profit divided by total sales. That's called percent of gross profit, and that's a metric that tells us how much is left over to cover fixed costs and profit. Now, instead of taking two measures and dividing, there's a great and convenient function in DAX called divide. It allows a numerator, that's gross profit, comma, and the denominator. And the reason we use divide rather than division, comma, is because this argument allows you to say what you want when there's a divide by zero error. And if we omit this argument, it will show a DAX blank, which either shows nothing in the cell, or if there's no data, it doesn't show that row in the report. Now we can add percentage number formatting. In the pivot table, I will simply check each one of these, and there are 4 more measures. If you're working over here in Power BI Desktop, here's the formulas, and there are the results. Now on percent totals, I've already started this pivot table, and I have a question for you. We can get the measure to see the filter context. So in this cell right here, it sees Eagle. The fact table is filtered down to just Eagle. But what if I wanted a measure to compare each one of these individual items to the grand total? How do I get a measure to do that? Well, I'd have to get the measure as it copies down in each cell to totally not see the filter context. And the function we're going to learn about now is called the calculate function. And it's the function in DAX that can change the filter context. Over in Power BI Desktop, you can start on this sheet. We'll start off with a measure called grand total sales. And I'm going to type the letter C. It's always the first function, so I hit C and Tab. And it has 2 arguments. Expression, this is where you put the measure where you want to change the filter context. Filter, that's where we put our condition, either an explicit filter or a filter modifier function. Now, we can have multiple filter arguments, and they'll all work in an AND logical test to change the filter context. Now, we want the grand total for total sales, or said a different way, we're going to use calculate to change the filter context for this measure as it goes down in the pivot table, comma. Now, filter, we'll see later, just like the filter function in Excel, how we can use a column, a comparative operator, and then some condition. But there's a bunch of filter modifier functions. Also, there's a bunch of date-related functions. Now, the one we want is we want the function that removes all filters in the data model. And the name of that function is all. Now, there's also an equivalent function that came long after all in DAX history. It's called remove filters, and it does the same thing. So you can use either one. Now, all can take a column, which means it will remove all the filters from that column, a table, which means it removes all the filters from that table. Or if you don't put anything, you just close parentheses, then all is programmed to remove everything in the data model. And that's what we want. Close parentheses. Now remember, calculate has a formula and then something that's going to change the filter context. Now when I hit Enter, add some number formatting. Of course, here it's no different than these measures up here that do see filter context, because in the measure grid, we don't have any filter context. Now over here in our pivot table, there's our formula. I'm going to check. It goes down to values. And lo and behold, the grand total is in every cell. Now, we want to learn something important about DAX. If we had worksheet formulas, notice, we could use cell references. All I'd have to do is, as a relative cell reference, take that, divide it by the bottom, and I would lock it. This is what Excel formulas do so amazingly. They're very versatile. We can point anywhere in the spreadsheet. Those are all the correct amounts. But when we get to DAX, we can't really point to a cell reference like that. So we're going to use total sales in the numerator. That way this will change based on the filter context. But this is the formula we have to use in the denominator. Instead of a locked cell reference, we have to create a formula that delivers the same amount in every cell. Now, you would never actually show this in a pivot table report, but when we're learning, it's very handy to see the visual output total in every cell. All right, so we'll do percent of total sales, and we're going to do division, so we're going to use the awesome divide function. Square bracket, total sales, that's going to see the filter context, comma, square bracket, grand total sales. That one is going to totally ignore the filter context. When I hit Enter, of course, over here, I get 1. We'll add some formatting. I better right-click Insert. When I click back in the pivot table and check That is a thing of beauty. The question is, what if I select, because this is a filter, right? This is going to affect everything in the pivot table. If I select Midwest, well, this percentage right here is doing exactly what we programmed it to. It's taking all of the filtered amounts and comparing it to the grand overall total with no filters from anywhere in the data model. But if we have a slicer like this, we might want, instead of the grand overall total, we might want the filtered grand total. In that case, we don't use all to remove everything in the data model. We use ALLSELECTED. And ALLSELECTED is programmed inside a report like this, or a visual, or a table in a formula, to remove all the conditions from the row and column area. All other filters in the data model are allowed to filter. It's just all of the items selected in the row and column area, those are removed. So let's try that. Expression is our total sales, comma, the filter. We're going to use another filter modifier function, ALLSELECTED. And same thing, we can use columns, tables, or if we leave it empty, it removes just the row and column from whatever report it's sitting in. Close parentheses, enter. And over here, of course, it's going to get exactly the same as all of these other ones because there's no filter context. Better insert some rows. And now let's see if filtered grand total will work. And lo and behold, that is a thing of beauty, the filtered grand total. If I change the filter out here, bam, it is working. And if we remove the filter here, then of course these are going to be exactly the same. For percent of filtered total, the only difference is in the denominator. We'll use filtered grand total and enter. And when we check to put it in our pivot table, that is working. And if we select a condition out here, bam, that is working fine. Now, percent of total and percent of filter total, you might want both because they both give us good information, but different information. Also, when naming these, maybe this is the only one you use, so you just call it percent of total sales. Now, the next question is, what if we want percent of parent total? That means each one of these values divided by the parent total. Here is advanced boomerang category. Down here is beginner. Now, when we want percent of parent total, we have a couple of options. And the first one is not all selected, but all except. For the table, we're going to say F sales. That's, in essence, all columns in the data model, comma, and the one we don't want, D product category. So this will remove everything. Remember, F sales has all columns. All the filters are removed, except for category is allowed to flow in and affect total sales. Close parentheses and enter. I'm going to unfilter this and select parent category total. And just like magic, look at that. There's the total in every cell. Same here. Now, if we add an external slicer filter, I'm going to select this right here. It's going to remove everything except for the one column we told it, category. Now, that may be what you want, but there's an alternative. In the next example, we'll use calculate, and we'll use ALLSELECTED, which is going to remove everything except for whatever column or row criteria are in our particular report or visual. But then we'll use not all, but values. Values, we can say, hey, please look at category, and values will add that back in as a filter. Now, before we create our final formula in this downloadable folder, we're going to open this file and look at the difference between all and values functions. Now, the all table function will remove all filters and deliver a unique list, whereas values actually sees the current filter context and delivers a unique list. So here's our finished report. I just want a list of sales rep name and then a list of all the products that a particular sales rep sold. We can see for Bob, there's 3 different products. There's our unique list. Now, the problem with all and values is they're table functions. So I can't really drop a table function into a cell because a DAX formula in a pivot table or visual has to deliver an aggregate result. So what are we going to do? We're still going to use all and values in two different formulas, but we'll use CONCATENATEX. That'll take all the values here and just the values in the current filter context. And from the product column, it will join them just as we see down here. Now, just as SUMX needs a table in the first argument to iterate across, CONCATENATEX also needs a table. We're going to give it all pointing to a single column, product, close parentheses. In every cell in the pivot table, all will remove all filters, so it will always see every single product, comma, and we need to give it a column that it's going to pick the values from, so the product column from that table, comma, and the delimiter will, in double quotes, use a comma, and enter. Now, the only difference here is we're going to use values instead of all. In every single cell in the pivot table, values will always see the current filter context. For the Bob cell, the product column will show just the three values. Values will look through and deliver a unique list from the product column and join it. If we drag our all DAX formula into the pivot table, in this cell right there, Bob would like to flow in and filter this fact table down to just those rows, but all on the product column prevents that. All removes the filter so that every single product is showing, and then all delivers a unique list. If we drag values, forget it. For every cell, that Bob condition is allowed to flow in. That means the fact table is filtered down to just 3 records. Values is looking at this column. It sees 1, 2, 3, and it delivers a unique list. And then, of course, CONCATENATEX joins them with a comma. So that's one way to visualize the all and values function. One does not see filter context, the other one does. So that's why when we use values to look at the category column as a filter inside of Calculate, in all of these cells, it will only see advanced. So values will add the advanced category back into the Calculate as an allowable filter. We'll create parent category total, all selected values. We have filter number 1 is all selected, comma. And now we're going to add a second filter using values, and we're going to point to the D product category column. Now we have 2 filters inside of Calculate. They'll be run as an AND logical test. All selected will remove row and column from the report. All other filters will be left untouched. Then values will add category back in. They'll be run in an AND logical test, and close parentheses and enter. I'm going to check this, and if we don't have any external slicer filter, we get exactly the same thing. But as soon as we add a slicer, this measure is removing only row and column conditions. However, this one's removing the row and column conditions, but then adding category back in as a valid filter, which is probably the denominator we want. I went ahead and created 2 parent category totals. This is one with all accepted. There's the denominator. Parent category using all selected and values. That's the measure we just created as the denominator. Now, if we unfilter everything from the slicer, add these two, we get exactly the same thing. If I add a region slicer, this one is looking at the denominator that doesn't see this. This one has a denominator that does. Over in Power BI Desktop, here's the result. There are all the formulas. Now, our next calculation, both here in Power BI Desktop and over in Excel, is going to be year-over-year change. We can go to this tab in Power BI Desktop or this tab over in Excel. Now, as we saw over here, we had to create a measure to show a particular value in every cell because we don't have cell references. If we think about a year-over-year change right here in February 2018, to get the change, I take the end amount, which is the current February, and subtract whatever last February was. Now notice I'm using cell references, and in DAX what I really need is the February amount, 26,312. I need it in the same row as February 2018. But somehow in the formula, I need February from the previous year. In this row right here, I have my total sales, but somehow I need to bring the total sales from the previous year. Well, what we'll do is we'll change the filter context. Right here, the fact table sees all the dates for February 2018. We'll put total sales into calculate, and in the filter argument, we'll use one of the amazing time intelligence functions in DAX. And the one we want is called same period last year. That means February will flow in, same period last year will push the dates back to February in the previous year, and then use that as the current filter context. So in the formula, we'll have total sales, and then we'll get this amount using calculate and same period last year. We'll call this measure year-over-year percentage change, and I'm going to build it in a few steps, but let's first look at just the same period last year part. We have calculate, we have the expression, comma, and in the filter argument, same period last year. And all it needs from the date table is the date column. So we give it the date column in same period last year. This will always supply whatever row it is, whether it's the month or the day or the year. It'll give me all the dates from the previous year. Close parentheses and enter. And when we add this to our pivot table, sure enough, it got exactly the correct amount, whether month or year, from the previous year. Now, when we complete this year-over-year percentage change formula, we're not going to do it in multiple steps like we did down here where we had a measure for grand total, and then we use that in a different measure. We want to try and build all the parts of the formula in one formula. Now, this sales amount from last year, we're actually going to have to use it multiple times in the same formula. Now, anytime you have repeating formula elements, it's helpful to define variables. Now, in M code, we saw how to use the let statement to define variables. In the Excel worksheet, we use the let function to define variables. But here in DAX, Alt, Enter, Enter, we use the VAR keyword to define variables. We start with VAR, and then a space, name of the variable, and then an equal sign. Everything after the equal sign is the DAX that defines the variable. Now delete, that will be our variable. Now we don't have to put a comma like we do in either one of the lets. Alt, Enter. We can define another variable, var this year equals, and we'll use our measure for total sales. Now I'm going to capitalize this, and you can define as many variables as you'd like. Once you've defined all your variables, then you use the keyword return. Everything after return is our formula that determines the output. Now let's calculate the change. And notice there's the icon for our variable, so I'll hit Tab. This year minus last year, and enter. Now over here in Power Pivot, this is a little clunky. This var appears on the first line. Over in Power BI Desktop, when you Alt-Enter, it'll stay on the second line. Here's the result, and it looks like for January 2018, if we check the difference, sure enough, it's minus 9 million. Now this formula shows us the amount of the change. What we really want is the percent change. So we compare the change to the total for the previous period. Now we'll do the division calculation, but there's a couple problems. Here, notice all of these amounts are exactly equal to total sales because there are no dates from the previous period, meaning before 2017. So it's total sales minus 0. Down at the bottom, it's the reverse. We don't have anything for these particular months yet, so it's 0 minus the amounts from the previous year. And then in the grand total cell, well, it's taking the grand total for every single year, 2024, 2023, all the way to 2017. But sales last year is as if we took this amount minus 2023 and before sale. So of course, we get exactly the total for 2024. So we're eventually going to have to amend the formula to show nothing there also. Now there's easy fixes for all those. But before we even do that, let's calculate percent change. So after return, we'll divide. So in the numerator, this year minus last year, and we compare it to last year. Now for 2017, since last year has a 0 amount, divide when it sees a 0 in the denominator will show nothing. So the values for 2017 will be removed. We'll hit enter and then add some percent number formatting. And now sure enough, that's not showing here. If we check, there's the amount divided by last year and enter. So we're getting the correct amount there. All the way down to the bottom, sure enough, 0 minus the amounts from the previous year. That's 100% down. Now, we'll solve this one at the end. But for now, what we really want to do is shut the formula off after the last day we have a sale. Now, instead of amending inside of calculate inside the filter argument, this is a situation where we can add a helper column in the date table, and it will be much easier than building the formula inside of calculate. Now, the logic of how this formula will work is we're going to ask from the fact table what's the last date with a sale. And because the part of the formula that's causing the trouble, remember, there's nothing here. It's actually the sales from last year. So if we know the last date is March 15th, 2024, if we push that back exactly 1 year, we'll get March 15th, 2023. And that's the last day that will be allowed for last year's previous sales. In the data model, we go to date, double-click to add a new column. Now I'm going to give it a long name, but a very explicit name that will be easy to understand. And let's first get the max from fsales, the date. This is an aggregate function and a calculated column, so there is no filter context. It'll just give us exactly the last date in every cell. Now this is 2024, and we need to push it back 1 year. So we use eDate. This is the same function that's in the Excel worksheet. We want to move back how many months? Minus 12. And that's our hurdle. Now all we have to do is say, hey, using row context, how many dates are less than or equal to this? So up in the formula bar, after the equal sign, there's the date column, less than or equal to, and enter. Now we get a logical column with trues and falses. And sure enough, when we get to 3/15/2023, there's a true, but 3/16/2023 and after gets a false. Now over in the pivot table or Power BI visual, filter context will, of course, filter the entire table. And only when it sees a true will that particular date be allowed. So in March 2023, 3/15 will be allowed, but not 3/16. Later, when we add sales, of course, then these will turn to true. Now we can use that column of trues and falses inside of calculate because it's the last year sales that we're trying to turn off. So we'll come to the end. Filter 1 is already there, comma, filter 2, date, and there it is. And the trues and falses from here, plus whatever dates are there, will be running an and logical test. And of course, any falses will cancel out dates there. When I hit enter and go look in our pivot table, sure enough, the formula delivers a blank, so those months don't even show up. Now, the only last thing we need to deal with is this because it's completely wrong. And in order to show nothing in a grand total cell, what we're going to do is we're going to notice a pattern. Now we have the year column in the row area of our pivot table. And for any cell, except for the grand total cell, whether it's year or month, the current filter context has exactly 1 year. It's only in the grand total cell that there are multiple years, all the years. So there's a well-known function to hide the formula in the grand total. It's called has one value. We'll use has one value on the date year column. Up in the formula bar, we say if, and in the logical test has one value, and there's the year column, close parentheses. When that comes out false, then comma, we want to run divide, and then at the end, comma, result if false is exactly like the last argument in divide. If it comes out false, the formula will show a blank. Close parentheses and enter. And sure enough, since there is no filter context over here, and this always shows us the grand total, there's our blank. And there's our completed formula for year over year percentage change. Now over here in Power BI Desktop, you can see the VAR stayed on the second line. Same formula, here it is in a matrix. Now so far in our conversation of Calculate, we've used filter modifier functions, and we've seen how to use a single argument, the filter. We've also seen how to use the filter arguments in Calculate to run an AND logical test. And we saw how to use the function same period last year and values to create a valid list of conditions. Now we would like to talk about how to add specific conditions to a formula using a Boolean filter. Now a Boolean filter just means, hey, we're going to take a particular column, a comparative operator, and give it a condition. That way it'll filter based on an internal condition we give it inside of Calculate. Now our goal with this measure is to calculate just quad sales. Then we'll use the measure over various conditions and criteria to look at quad sales. I type a comma, and in the filter, I'm going to type D product. We're going to select the products column. We use a comparative operator. I'm going to use equal sign, but any of the other comparative operators will work in a Boolean filter. Then because our condition is a product named quad and it's text, we put it in double quotes. There it is. That's a Boolean filter. And what it does is it will filter the fact table down to just quad. Now close parentheses, add some number formatting. There is no filter context down here, but that's the correct total for all quad sales. Now on the sheet Boolean, either in the Excel file or the Power BI desktop file, I've started 3 different pivot tables, and they're all filtered for the region W. We're going to start with this one. We'll check quad sales. That B is for Boolean. And when I check, now I have a quad sales report based on sales reps from the West region. And the great thing about having a measure like this is I can use any condition or criteria. And when I check quad, now I have a yearly quad sales report. Now, if we think about how this calculation is made in terms of filter context, there's actually 3 different conditions filtering the fact table before the calculation is made. From the date table, 2017 is filtering the fact table. From the sales rep region column, West is flowing in and filtering the fact table. And then from inside Calculate, quad is also filtering the fact table. Now here in this cell, because Alicia is assigned to the West region, and these are both coming from the sales rep table, there's really 2 conditions here. Alicia flows in and filters the fact table, and then from inside Calculate, quad filters the fact table, and we get the sales for the quad product sold by Alicia. For the Alicia quad sales, quad flows from the product table across the one-to-many to the fact table and filters, and then Alicia from sales rep across the one-to-many filters the fact table, and then based on both conditions, the calculation is made. If we look at page 24 in our PDF notes, we have the internal filter context coming from inside of Calculate, products equal quad. The external filter context comes from the row area of the pivot table, sales rep equals Alicia. Both of those conditions are running an AND logical test to filter the fact table down to just the rows for those 2 conditions, and then the final number is calculated. Now we have a product report, and I've filtered it just to show a few of the products, but these are products from the West, and we're showing total sales. Now let's see what happens when we drag quad sales down to values. We get exactly the same amount, the quad total, in every single cell. And the reason this is happening is because of the overwrite operator inside the calculate function. And what that means is there is the product column being used internally and externally. This one says product equals quad. This one says product equals Aspen. And when there's two columns, both externally and internally, the internal one wins. So this is not Aspen, it's quad. This is not Butte, it's quad. Now to understand the overwrite operator inside of Calculate, let's look at page 25 in our PDF notes. Internally we have quad. Externally we have two filters, product equals Aspen and region equals West. The very first thing that the overwrite operation does is it lists all filters. So products equals Aspen and region equals West. And then internally, products equals quad. Step 2, this is where it removes column filters from external that are also in internal. So it just flat out crosses this out. It's no longer a filter. Then there's one filter from the external, one filter from the internal. And they are running an AND logical test. Region equals West and product equals quad. Now on page 34 and 35 in our PDF notes, understanding how the overwrite operator works will help us not make a mistake when we're doing a complex filter. And we'll check this out later. Now here's our Boolean condition inside of Calculate. And to understand what's happening behind the scenes to get the overwrite operator to work, we want to check out this formula here. Now this is the actual formula that's run by the DAX engine when we create a Boolean filter like this. But understanding how this works will explain the overwrite operator. Now this is a new function, filter, and it works exactly like the worksheet filter function. There's a table that we want to filter, and in the second argument, there's our condition for filtering. But the trick to the overwrite is all. As we've already learned, what does all do? It removes the filter context. So because we put a single column, the products column, it's going to remove all external filter context and return a unique list of all the products. Then the second argument says, I only want quad. Filter delivers a table with a single record, quad. And that serves as a valid set of conditions or criteria in filter. And so now Calculate knows to only use the records for quad. And if we use this over in the pivot table, it'll give us exactly the same result. But we're glad we don't have to create that formula every time because we can do a simple Boolean filter like this. Now just as a quick note about the filter function, I'm in one of the files you can download. But over here in Power BI Desktop, you can actually use filter to create a table. This is the table over here, and this gets loaded to the data model. Now, we definitely use table functions like filter over in Excel, but they're usually in other functions like SUMX and calculate. If we look at the filter screen tip here, there's only one argument for filtering. So whether you're creating your filter function in Excel or Power BI, if you want to do an OR logical test, then you use the double bar. If you want to do an AND logical test, you can use the operator for AND, double ampersand. And finally, I want to compare the filter function to the calculate table function. Now, calculate table has all of the same properties and characteristics as calculate. It changes the filter context. Notice we have F sales. And with calculate table, you can pick any column in the data model to filter the fact table. And it uses the underlying filter mechanism to get to the final table. However, the filter function, whatever table you put into the first argument, in the second argument, you can only use columns from that table. And the way it filters is this is an iterator function like SUMX. It iterates down every single row to find product ID equals 2. If you ever have a choice between calculate table and filter, the filter function is probably going to take longer to calculate because it has to iterate down every row, whereas Calculate Table just uses the underlying filter mechanism to get to the final result. And as we'll learn later when we talk about context transition, Calculate Table does context transition, but Filter does not. Now later in the video, we'll see a great trick for Calculate Table over in Excel to extract data from the data model into the Excel worksheet. Now what if you wanted a filter like this, but you didn't want the total quad sale to show up in every single cell when products is in the row? Well, remember what caused quad to show up in every cell? We ripped away all the filter context using all. So instead of all, if we were to create a formula like this using values, well, values sees the external filter context. So in the Aspen cell, that Aspen condition would flow into this products column. Values would deliver it as a single record table, Aspen. Quad would try to filter it. And since there's no quad in an Aspen table, filter delivers an empty or blank table. That lets Calculate know to show nothing in the cell. Now this formula is not what a Boolean filter does. This is the formula we would create if we wanted this result. So if we drag filter values into our pivot table, bam, empty cells everywhere except for the row that has a quad. In this cell right here, the Aspen condition flows in, values delivers an Aspen table. The internal quad tries to filter it. It gets filtered down to an empty table, and we see a blank. But here, value sees quad. The filter says, hey, I'm going to filter to quad, and bam, we get quad sales. Now, as we'll see later, this technique right here, or another technique using KEEPFILTERS, will be handy when we want to create filtered reports without using filter. And we'll see that in just a moment. But I want to show you an easier way to accomplish this using a function called KEEPFILTERS. All right, so this is the KEEPFILTER version, and we have the same exact filter on product based on quad. And if we wrap the function KEEPFILTER around it, and notice the screen tip changes calculate and calculate table function filtering semantics tab, what it will do is it will convert the overwrite operator to an AND logical test. So now when it gets to the Aspen cell, rather than quad internal replacing Aspen external, that is running an AND logical test. Is the product quad and is it Aspen? Well, there are no records that are simultaneously quad and Aspen. So the fact table is filtered down to 0 rows, and a blank is shown in the cell. However, when you get to the quad cell, there's external filter quad, internal filter quad. They're running an AND logical test. Only quad records are showing in the fact table, and the total for quad is shown in the cell. Now here's our quad KEEPFILTER. When I check, sure enough, much easier way to accomplish the same goal. Now, this type of formula right here can be handy when you have a group of criteria and you want a self-filtering report. So now we're going to go look at how to do an OR logical test inside of Calculate, and then how to convert it to a self-filtering report using KEEPFILTERS. Now, the goal of this measure is to calculate total sales for the trick catch category. Now, we do have a category column in our product table, but this isn't one of the attributes listed. So because Carlota and Quad are the boomerangs that make up that group, what we'd like to do is do an OR logical test. In the products column, we want to say, please give us Carlota or Quad. The problem is, if we use the arguments filter1, filter2 inside of Calculate, those run an AND logical test. Now, the way we can deal with this is just use one argument. And we use the OR operator double vertical bar. Now, when I hit Enter in the measure grid with no filter context, there's the total for trick catch booms. Now, there's an alternative. you can use the OR function inside a filter, but for some reason, the OR and AND functions over here in DAX only take 2 logical tests. That's much different than the Excel worksheet where we have over 200 logical tests. Now over here in our pivot table, because these are Boolean, when I check both of them, we get the same amount in every single cell. Total sales in region West. Now if we want this to be a self-filtering report, we just use KEEPFILTERS. That will convert the overwrite to an AND logical test. And so now over here in this new pivot table with all the products, when I check trick catch with KEEPFILTERS, bam, a self-filtering report. Now this pivot table is not connected to the slicer up here. So in the grand total cell, that's really Carlota or quad sales. However, remember we used KEEPFILTERS. And because there's an external filter and some internal filters, those will be running an AND logical test. So here's how it works. Is product equal to Carlota? True. And is the first condition in here, as part of the OR logical test, is product equal to Carlota? True. So we get a true there. Then it moves on to the second part of the OR. Is product equal to Carlota? True. And is product equal to quad? False. So we get a false. So in that cell, we get only Carlota. Here, we get only quad. Now, this is a self-filtering report, and we only have 2 items. But by all means, we can have more than 2 items. Now, this is going to be Aussie round boom sales. That's an awesome competition event where you get points for boomerang distance, accuracy, and catching. The boomerangs in that group are flat top, or sunshine, or sunset, or butte. Now we can definitely use the double vertical bars, but an easier way is to use the DAX in operator. So if we look at this formula, we're still using KEEPFILTERS. Inside we put the full column, the in operator, and then in curly brackets the OR conditions. So now for this pivot table, when we drag either one of those Aussie round boom measures in, bam, a self-filtering report. Now next, let's look at a not logical test. Now for this measure, we want everything that's not in the Aussie round group. Now I'm going to keep KEEPFILTERS on the outside. Everything on the inside is the OR logical test. So I just put all of that inside the not function. Not the mot, but not, close, and enter. Now in this new pivot table, we're going to drop our not, and there's a self-filtering report for items that are not in the Aussie round group. All right, that was a lot of fun with Boolean filters. We saw how to create Boolean filters. We talked about the overwrite operation inside of Calculate. We talked about KEEPFILTERS to convert overwrite to an AND logical test. And we talked a bunch about OR logical tests and KEEPFILTERS to create self-filtering reports. All right, now perhaps the most important topic in this whole video, let's go talk about context transition. Now, context transition is one of the most amazing features of DAX, and it brings great power. Now, there is a danger with context transition, and we'll learn exactly how to avoid that. Now, in Power BI Desktop, there's the context transition sheet. But in both Excel and Power BI, we're going to start over in the tables, and we want to look at the product table. Over here in Excel Power Pivot, we want to go to the D product table. And we're going to create some calculated columns because our goal is for each product to get total sales, and then I want a % of total sales. Now remember, this is a calculated column. It definitely has automatic row context, but it doesn't have filter context. So with that in mind, let's create our first calculated column to calculate total sales for each product. Now we're going to double click, and I'm going to call this one sum. Up in the formula bar, we want to sum F sales, line sales. Now this is an aggregate function, so when I hit enter, I get the same grand total in every single row. And it is because, yes, there's row context, quad, Yanaki, but there is no filter context. So inside an aggregate function in a calculated column, it's never going to see quad and have that quad condition filter the fact table. Now, in our date table helper column, remember we already used an aggregate function max. And in every single cell, we had the last sales date. Now, in that column, that's exactly what we wanted. We didn't want filter context. But here, we want the quad to flow in and filter the fact table. Well, the way you convert row context into filter context is you use the function that changes the filter context. Now I'm going to call this calculate sum in sum F sales line sales and enter. Well, of course, I get the grand total in every row. But as soon as I wrap calculate around sum, and notice sum is sitting in expression, that's where we put a formula where we want to change the filter context. Remember, there is no filter context, and we want to change that. In every single row, we want the row context condition, in this case quad, to flow in and filter that fact table. So when I close parentheses and enter, just like that, every single row has the correct total sales for the given product. In the Aspen row, Calculate said, hey, I know there's row context there, so I'm going to change it to filter context. That fact table sees only Aspen records, and of course, that's the Aspen total. Now, we use Calculate without the filters. If you had a situation where you wanted filters, then context transition would bring row context into filter context and do an AND logical test with whatever filters you might put in. But for us, we don't want any filters. We're just using Calculate to do context transition. Now, a calculated column in a table is not the only place the context transition occurs. Remember, this is a table. We are iterating row by row to make a calculation. Well, where else does that happen? In iterator functions like SUMX, AVERAGEX, and add columns. Now we'll see awesome examples of AVERAGEX context transition, which makes formulas simple in just a moment. But let's learn something else about context transition. I'm just going to call this hidden calculate. And up in the formula bar, I'm typing a square bracket, so that means I'm about to put a measure. We're going to put total sales, and when I hit enter, what? The measure automatically converted row context into filter context? You betcha. Here's the thing. Every time you create a measure, any measure in Power Pivot or Power BI Desktop, it has a hidden calculate wrapped around it. That means anytime you use a measure anywhere, if there's row context available, it will be converted to filter context. And if you don't want your measure to do context transition, then you use the formula inside the measure instead of the measure. And we'll see an example of that coming up. So this measure in the Carlota row, that hidden calculate says, hey, row context Carlota, I'm going to bring you in, and inside the measure, the fact table is filtered down to just Carlota records, and that's the total sales. Now, before we use this measure trick to do amazing things inside of iterators, let's create one last column. We'll call it product percent of total. And up in the formula bar, I'm going to use a measure. That means there's definitely a hidden calculate. That will see the row context in every row, convert it to filter context. But what do we do when we have product sales? We need to compare it to the grand total. So this part of the formula, we absolutely do not want context transition. We don't want filter context. We want the grand total. So we're going to just use the sum function. Any aggregate function won't do context transition. And when I hit enter, there's the product sales as a percent of total sales. In this calculated column, we used a measure with a hidden calculate to do context transition. But in the denominator, we just used an aggregate formula to get the grand total. All right, now we want to go over to F sales and see how to use the X Iterator functions and context transition. Now, over on the context transition sheet, before we create our average monthly sales measure, let's see how to do it the long way. Now, this is a data model pivot table. From the date table, I dragged end of month. That means we have a unique list of every single month. Then I drag total sales. This represents the total sales for each month, every single month. And then I filtered it to show just the monthly total for Aspen. If we wanted to calculate the average monthly sales for Aspen, we'd have to do all of these steps here before we could calculate the final answer. That's the average monthly sales for the product Aspen. Now, when we get over to our measure, envision this table. This end of the months will create this unique list with the values function. That will create a table. We'll put it into the first argument of AVERAGEX, and then we'll run the measure using context transition to calculate every single total sales. And then from those sales, we'll calculate our average. So we'll keep this picture in mind and go create our measure. Now we'll call this measure average monthly sales. The Aspen condition will always come from the outside filter context. We're going to use AVERAGEX. And in the first argument, we need a table. And we need that table to always see the current filter context. So instead of using all to get every single month possible, we're going to use values. And because we want a unique list of months, we're going to use date end of month column. Now, when I close parentheses, what values will do is when it's in the Aspen cell, it'll just deliver a unique list of every possible month. But if we drag this formula into a pivot table with year on the row, when it gets to the 2018 cell, what we want there is the average monthly sales in 2018. Values will see the external filter context of 2018 and deliver a table with the 12 months for 2018. Comma. In expression, we want our total sales. And yes, it has a hidden calculate. And yes, it's going to do context transition. Now, if we're in the Aspen cell, Aspen will flow in and filter total sales down to just the records for Aspen. And then, as the measure iterates over all of the possible months, remember row context, when it's in the very first month, that end of month condition with whatever number of days will flow in and filter the fact table. So it'll be Aspen records for that particular month. That'll be the first sales. Then when it gets to the second month, that set of monthly dates will flow in. It's Aspen records only for that month. It continues doing that until it has every single Aspen monthly sales. Those are the internal sales numbers that then the average part of AVERAGEX uses to make the monthly average for Aspen calculation. All right, enter. Here's our pivot table with product on the row. I'm going to check way down at the bottom, average monthly sales. And bam, there it is. In the Aspen cell, no problem. Aspen filtered the fact table. That measured it every single row, got the monthly sales, and gave us average monthly sales for Aspen. Down here, average monthly sales for Kangaroo. And it gets better. This is a totally different calculation. We didn't do anything different to that formula. But when I drag it into the pivot table, now we have average monthly sales for each year. In the year 2021, the average monthly sales, 60 million bucks. When the values function inside the first argument of AVERAGEX sees 2021, there's only 12 months there. And that measure goes down 12 months, calculates the total sales, and then the average is calculated. And what makes this formula so amazing and illustrates the power of DAX over our other formula languages is in every single cell right here, we skipped over a bunch of complex calculations just for Aspen, but then we skipped over the complex calculations for Butte, all of these, and then we just dragged the measure into a totally different pivot table with a different condition on the row, and it calculated the correct result. Now, to take a closer look at what's happening in that cell, let's go to the sheet Aspen Monthly Sales. Remember, we have total sales. That's in the second argument of AVERAGEX. But from the external pivot table or visual in Power BI, Aspen flows in and actually filters the fact table down to just Aspen records. And then that's used, those Aspen records, in the second argument for every single row for the end of months. But the end of months are generated by the values. It's this entire list. And then when this measure starts iterating, when it hits the first row, the context transition from the hidden calculate brings more conditions than just Aspen. It brings this into total sales. And remember, in the date table, we have lots of repeats for the end of January 2017. So all of these dates are allowed. Finally, the F sales is filtered down to all rows for January 2017 for Aspen cells. And that's just in this cell right here. So the total sales just for that cell is 1.3 million. This process happens in every single row, all of these amounts here. And then step 7, that's where the average, and AVERAGEX takes all of these amounts and calculates the final average. So now we see the power of DAX to use context transition to make a calculation like average monthly sales. However, there's a big caveat, and that is for whatever iterator you're using, SUMX, AVERAGEX, the table in the first argument must contain a unique set of records or a primary key. Because if there are duplicate records, you can get into big trouble. And that's what we want to look at next. Now, in our data model, we have 4 tables. 1, 2, 3 dimension tables and a fact table. Well, each one of the dimension tables has a primary key. So there are unique records in all 3 tables. But the fact table has duplicate records, and there's no primary key. Now in data view, I actually filtered this table to show you the duplicate records. But when you filter, it affects these numbers here, so they're off. Later when we unfilter, these will be back to the grand totals. In a fact table, it's common to have duplicate records. For example, we have 1/1/2017, product 1, sales rep 3, units sold 7, cost of goods sold 131.06. And there are 2 records with those exact matching elements. That means if we invoke context transition over the fact table, we're going to get formulas that deliver the wrong answer. Now, we already iterated over the fact table, but notice we used a formula. And that's the rule. If you're going to iterate over a table with duplicates, don't use a measure, use a formula. Now, to see why duplicate records cause an error, I went ahead and created this calculated column. I used the total sales measure and copied it down. I was hoping to get exactly the same as line sales, but no, I got double the amount. And here's what context transition did. When it got to this row, it saw all of these elements that it thought was making up a unique list. So instead of the fact table being filtered down to just this row like it was here, it actually saw both rows. So in this row, it took both of these rows and calculated that amount. Then when it got down to the other duplicate, it did the same thing. Filter context, filter this table down to 2 rows, and we got twice as much. So whether in a calculated column like this or an X iterator, if there's duplicates in the table that you're iterating, don't use a measure. Now let's look at 3 examples. We want to calculate average transactional sale. Now earlier we calculated average monthly sales, and we had to add the total monthly amounts before we averaged. But if we're doing average transactional sale, we just take the amounts from each line, which represent a transaction, and average them. So if we want to average, and we already have this column, we just use average. But what do we do if we don't have this column? Well, like SUMX, we'll use AVERAGEX. And that fact table definitely has duplicate records. So what do? We use a formula rather than a measure. That's the formula to calculate the line sales for every row in the fact table. Here's what we don't want to do. Table with duplicates, measure, we're in big trouble. In essence, what's happening is the process is creating this column. So you can clearly see for both of these records, they have transactional amounts that are too big. So the average result is incorrect. Here's a pivot table with supplier, and we're going to check the average transactional. C is for the column we used. Average transactional. F is for the formula. That's what we want. Uh-oh. The M is for measure. And all of these amounts are completely wrong. And this really is the invisible part of DAX that is sometimes so frustrating for people. Because they're like, well, I have a measure, so I'm just going to use it in the second argument. And really, with big data like this 2 million rows, it's hard to see or even detect that there's an error here. But for us, it's never going to be a problem. If we use a measure and invoke context transition, it's always going to be over a table with a unique list or a unique set of records. Now, you could add a primary key using Power Query to the fact table, and then you wouldn't have this problem. But adding a primary key to a fact table is almost always a terrible idea. And that's because the Columnar Database stores a unique list for each column. And our table is 2 million rows. So that column it's saving underneath is 2 million rows. And I'm not going to do it in this video, but if you test it, our file size just blows up. Now, it's not just context transition that makes this a terrible formula. Yes, the first problem is that context transition will cause calculation errors. But the second problem is we're iterating this measure over a fact table with 2 million rows. But inside this measure is SUMX. And that iterator is iterating over a fact table. So we have iterating over the fact table for each one of these 2 million rows. That's why it took so long to calculate when we dropped it into the pivot table. The third reason that this is a terrible formula is, guess what? This formula doesn't even need context transition. If we look at the formula, these two columns are already looking at each row in the fact table, so we absolutely do not need context transition. So for a formula like this, context transition causes calculation errors. It will take too long to calculate in the pivot table, and we don't even need context transition in the first place. Now, our next DAX topic is grain. And that just means what size is the number before you make your aggregate calculation. For example, we've already made 2 average calculations where the numbers had different sizes or different grains. For example, when we did average monthly sales, the grain was at the month level. When we calculated average transactional sales, the grain was transactional. And definitely one of the more amazing things about DAX as compared to the other formula languages is how easy it is to create tables at different grains. Now, for average transactional sales, we had a table in the data model that had the correct grain. That's the F sales table. For the average monthly sales calculation, however, we did not have a table with the correct monthly grain. But no problem. We used values on the end of month column to create the table with the correct monthly grain. But what if we want average daily sales? Where are we going to get a table with a unique set of dates? Well, luckily, one of our dimension tables, DDate, that has a primary key with a unique list of dates. So because there's a unique list of dates, comma, we definitely can use a measure to invoke context transition. Whatever's in the external filter context will flow in and filter the fact table. Then, as it iterates down each day, for any particular day, that date will flow in and filter the fact table. And that will create all the daily sales numbers required to make the average calculation. And now enter. Now, with whatever attribute we have in the row area, I have products. Now we can say, hey, what's the average transaction for each product? No problem. Average daily sales, there they are. Average monthly sales, bam. So for quad, the average transaction is about $4,000. The average day is about $500,000. And the average month is about $16 million. Now, interestingly enough, when we get to average daily sales, this is not the only way we can create this measure. When we did average monthly sales, that pretty much is the best way that I can think of to make that calculation. But guess what? Since average is really add them up, divide by the count, because there's a date attribute column, actually a foreign key in the fact table, we can simply use total sales measure in the numerator, and in the denominator, the amazing function distinct count, looking at the F sales date column. Now we'll use the divide function, and in the numerator, we'll do total sales, whatever external filter context there is, it'll flow in and filter that, comma, and the denominator, we'll use distinct count, and it's got to be F sales, there it is, date, and the external filter context will also flow in and filter this. Close parentheses, that's the denominator, close parentheses, and enter. Now, if we look in the measure grid, we're going to get the same answer here, and we'll get the same answer in whatever pivot table we use. But whereas this is iterating, and then internally there's a fact table, this is a lot more calculation intensive than simply using the measure in the numerator and then using the particularly fast calculating distinct count function. Remember, that function works with the Columnar Database, and the Columnar Database already stores everything in a unique or distinct count list. And if you time the two formulas, this one definitely calculates more quickly. And when we drag this measure into our pivot table, we'll get exactly the same result with either formula. Now, with constructing alternative formulas to try and get faster calculating formulas in mind, let's open another one of our downloadable files. Now, here's a picture of our data model. Here's the fact table, and we have two dimension tables, date and product. Now, our fact table has 21 million rows. That's a lot of rows to iterate over. Our date table has 730, and our product table has 630. So what if we could iterate over 630 rows instead of 21 million rows? That would be a lot faster. Not only that, but what if we could iterate over the price column? Because look at this, there are lots of repeats for prices. Now we'll see two alternative formulas, one where we'll iterate over the full product table, and another one where we iterate over a values generated unique list of price. So what we want to consider is cardinality, and that just means the count or the number of elements we're iterating over. If we can reduce the cardinality, then the formula tends to run faster. If we look at our data model and think about what it is we're using to calculate total sales, well, we're using units and price. From the fact table side, we just look up price, match it up with units, iterate over 21 million rows. But what if, for each unique product, we could bring total units over to D product? If we're iterating over the product table, how do we get total units? Well, we do it the same way as we got total sales in a calculated column over the product table. There we summed line sales. It gave us aggregate, but all we had to do was put calculate in front of it to convert row context to filter context. So that's what we'll do over here. We'll do sum of total units, put calculate in front of it, and then bam, we have the price for one of the 16 products, the total units, and that will be a faster way to calculate total sales. We can do the same thing for price, and there's only 7 rows. So we'll calculate total sales, iterate over the product table. We want to use values so it sees the filter context. We're going to use the whole D product table, comma. Now, comma, the formula, well, what column in the D product table do we want? We want price times, and we would like to just say, hey, sum F sales units, But of course, that's aggregate all the way down for every single row. So to bring the particular product row context into the fact table, we use calculate. Now, row context is converted to filter context using context transition. When I come to the end, close off SUMX and enter, I get exactly the same number as if we iterated over 21 million rows. Now watch this. We can do even better because this is iterating 630 times. I'm going to paste this up here, change iterate product to iterate price. Because this formula needs to be looking at a column in this table, well, dProduct had all the columns, and we really only need price. So if I square bracket and put in price, guess what? The maximum number of prices that values are ever going to deliver are 7, because that's how many unique prices are in that column. So we have a table with a unique set of records, in our case, price. We're using a column from within that table, and then we're using context transition to get total units. So when I enter, I get exactly the same answer. 21 million iterations, 637. Now this calculates total sales. And in our next formula, average transactional sales, keep this in mind. Here's average transactional sales iterating over 21 million rows. It's just look up price and then get units from the fact table. But check this formula out. Just as we did before, we're going to use divide. And in the numerator, we're putting total sales. And there it is. That's the version with, at a max, iterating 7 times. And because we're calculating average transactional sales, whatever filter context flows in, it'll filter the fact table down to the correct number of rows, and count rows will count. So divide total sales by whatever the count is, and bam, we're going to get exactly the same number, and we're not going to have to iterate over 21 million rows. Now I went ahead and created a pivot table with our 3 total sales measures, and when I timed them, we'll call the 21 million row formula base 0. But for the 630 iteration formula, there was a reduction in calculation time of 20%. For the 7-row formula, there was a reduction of 32%. For the average formula, 21 million rows with base 0. And when we used our alternative, there was a reduction in calculation time of 35%. Now what this means is because in DAX, big data is a big component. When you get big data, it pays to know the structure of your data model and the type of data you have. Because sometimes you can make formulas that calculate more quickly. And for big data, that matters. Now, how did I time these DAX formulas? Well, I went to Google, I typed in DAX Studio, and then downloaded the free app. Once you install it in Excel, you go to the Add-ins tab and click the DAX Studio button. If you're in Power BI Desktop, you open the file first, then open DAX Studio, select Power BI, select the file, and click Connect. I'm going to do the timing from Power BI Desktop. I'm going to click Connect. Over here, we can see our tables. For example, here are the measures from F sales. Up in Home, I want to clear and run. That means every time we click Run to Time, it'll clear the cache. And over here, I want Server Timings. And come over to Server Timings. And the way we have to do things over here in DAX Studio is everything has to be a table. Well, a measure isn't a table, but that's not a problem. We will use the row function and create a 1-column, 1-cell table with our measure. And you always have to start your queries, DAX table queries, with the evaluate command. Enter, and we'll use the row function. It requires 2 arguments. The field name is text. I'm going to call this total sales iterate fact because that's the measure I'm going to time, comma. And then I can come over and double click the measure, close parentheses, and enter. Now you have to do this for each one of the measures. But once you have a 1-column, 1-row table like this, we can click Run. And we get a total of 12 milliseconds. Now, 2 milliseconds was spent in the formula engine, 10 in the storage engine. And the storage engine calculates much more quickly because it uses multiple processors. For example, that is why the distinct count function works so quickly, because the calculation comes from the storage engine. And of course, you can time all your formulas, and we can see the iterate price is much quicker. Now, we'll come back to DAX Studio later when we learn how to extract data from the data model in Power Pivot into the worksheet. Now, the next topic we want to talk about is a complex filter and a complex filter reduction error. Now, a complex filter just means we're running an AND and OR logical test together. This is something you might create externally in a pivot table or in a Power BI visual. And a complex filter reduction error happens when you do this in the external filter context, and inside the measure, you're using the same two columns, year and month, and it's the overwrite process in Calculate that causes the problem. Now, here's an example of a DAX formula that causes a problem when you have that external complex filter. And here it is. This formula uses year and month. Now, this is not a good way to do average monthly sales because, as we've seen already, it's much better to create a helper column in the date table and then use values to get a unique list of months. That's what cross join is doing here. It's joining year and month together to create a unique list of months. The problem is, when we drop this measure into a pivot table or Power BI visual, the internal filters will replace the external filters. And what cross join is doing, it sees the 2 years in the filter context and the 4 months. But a cross join matches up each year with all 4 months. So instead of getting the correct from the external filter 4 different unique months, we get 8. And since this table that's going to be used to iterate is inside the formula, this will replace the external filter. And for this example here, it's only the grand total cell that gets trouble because the filter context has both years and all 4 months. So if in fact you have a formula like this and you want to use it, what you do is you use KEEPFILTERS, because KEEPFILTERS converts overwrite to an AND logical test. And an AND logical test on 8 unique months and 4 unique months, well, only these 4 will be over here. So the AND logical test will remove the unwanted rows. But of course, this is all unnecessary because really, we just use a helper column in the date table, values, and this is a much easier formula. Now, the reason that I'm showing you this is because of an automatic feature in Power BI Desktop where KEEPFILTERS sometimes shows up. Now, when we create a measure, we right-click New Measure. Now, there's this option, New Quick Measure. It will build formulas for you. I don't use it because I like to have complete control over what I'm putting into my DAX formula. And as we'll see, sometimes it creates unnecessary elements. Let's try it. The calculation we want is average per category. From the date table, I'm going to drag the correct end of month. That's the category. And then we'll drag total sales to base value. Click Add. And whoa, there it is. It looks pretty good. It's got the average X part. It's got the values on end of the month. And it's got the measure. Now, it puts KEEPFILTERS in because it wants to avoid a complex filter reduction error. But see, the thing is, we used a column where this will never be an issue. So KEEPFILTERS is not needed in this formula. Also, they want to make sure that whatever you put here does context transition. So they put an unnecessary calculate. But there you go. Now, if you see this, you know what it's there for. Now, the next topic we want to talk about is a moving average. On the sheet, moving average in the Power BI Desktop file. Or in the Excel file, we want to see how to take a chart like this. This is a line chart, and the sales are very volatile. So it's hard to see the overall trend up or down. One way to solve this is to create a moving 12-month average. Then when we plot it, it smooths out the sales and we can see the overall trend. Now in the Excel worksheet, of course, we can use worksheet formulas and relative cell references that always look from the current month 12 months back. And of course, with relative cell references, when we copy it, it's still looking 12 months back. But in DAX, how are we going to do that? Well, the filter context right here is January 2019. And what we really want is we want to change that filter context. So instead of just January, it's January all the way back to February. And of course, the way we change the filter context is with the calculate function. And we'll use a great function called dates in period, which will allow us to take January and stretch it all the way back to February. I've created a variable, calculate, there's the average. And in filter, we're going to use dates in period. Now the dates argument, just like same period last year, uses the date column from the date table, comma, the start date. That's going to be whatever the maximum date is in the current filter context. So in February, it'll give us the end of February. Close, comma, number of intervals, we want to go back 12 months, comma, and the interval is month. And we close on dates in period, close on calculate, Alt-Enter, return, Alt-Enter. There's our new variable, Tab and Enter. We can check our measure, and now we can see the overall trend down, up, much more easily than we can with our volatile sales lines. Now I added a 2017 filter here. If we add it back in, the problem with our numbers from the measure is we don't have the dates from before 2017. So this is meaningless. Now over here in Excel, we'll just use the filter feature in the pivot table. When we get over to Power BI Desktop, I'll show you how to amend the formula. But we need to turn the line off after it gets past the last sales day. And the way I'm going to do this is I'm just going to ask for the max sales date from the F sales date field. Now, when we get past March 16th, as we saw in one of our earlier formulas, there are no sales. So max conveniently will return a blank. Now, let's just see what max returns when I drop this in the pivot table. Now, there's the max date for any given filter context. But look at that. Because it returns a blank, all of these rows don't appear in the pivot table or visual. So now we use the if function and put max into the logical test. Because dates are really numbers, and if interprets any non-zero as true, all those dates will be true, comma. If it's true, we want to put our moving average. Otherwise, then result if false, that will deliver a blank. Sure enough, there's the moving average. And there it is in the chart with no line past the last sales date. Over in Power BI Desktop, you can see I left 2017 in the visual. And because Calculate allows multiple filters, what I did is there's the first filter. And the second filter, I did a Boolean filter on the year column to say greater than 2017. So with our DAX formula in Power BI Desktop or in Excel, we have our 12-month moving average to help reveal the overall trend. Now our next topic is how to use a table filter to go backwards across a one-to-many relationship. Let's open this file. And what we have is we have a dimension table with compressors. Here's the supplier. Over here are the sales. And compressor sales are sparse, so they don't happen every month. Now here's our F compressor table with the sales, dimension tables. This is where the filter in the pivot table is going to come from, supplier and compressor. And it has no problem flowing across the one-to-many relationship. But really, we're going to have to look at end of the month column and count how many there are in the current filter context. But the problem is the filter can go to the fact table, but how do we get the filter across the many-to-one relationship, which does not happen automatically? Now we'll call our measure unique months transaction occurred. And we're counting, so we're going to use count rows. In the table, well, we want the end of the month in the current filter context, so we use values, and from the D date, end of month. Close, close, and enter. Now we can try our new measure. When I check, we get the grand total in every single cell. When you see this, it almost always means whatever the filter is isn't making it through the relationship. Now, as we saw earlier in the class, here's our expanded table diagram on page 36. And this will give us an answer of how to filter end of month using supplier and compressor. Now remember, the fact table really has every column from the data model. So sure enough, end of the month is already in F sales. So the trick is, since supplier and compressor are already filtering this, we'll just put the table, the entire table, into the filter argument of calculate. And because end of month is there, we'll get the correct count. We'll call this unique months transaction occurred table filter. And the function to change the filter context, calculate. Now I already copied the formula from here. So Control V into expression, comma. And what do we use? We're going to use the whole F compressor table as a filter, close parentheses, and enter. Now the grand total is 44 because not every single month from the date table had a compressor sale. So we'll check our new measure, and bam, there it is, the unique count for each compressor and supplier of months where we sold a compressor. For air bubble, it was 26, rotary, 7, and the total for Bay Air Services, 30. So anytime you have a field from a dimension table and you want to get a filter from one of the other dimension tables, we can just use the full fact table as a filter. Now for our next topic, we're going to open up unmatched items. Now the term unmatched item in a relationship means there's something in the fact table that's not in the dimension table. There is a relationship, dimension, fact. And what happens in a pivot table is different if you drag product from the dimension table into the row area of a pivot table, or you drag product from the fact table. Now to see this in action, we're going to mistakenly drag product to the row, because really we should have hidden this in the data modeling phase. Product down to row, units, and it's looking pretty good. We have Aspen, that's an unmatched item. But now if we correctly drag our field from the dimension table, which is what we should be doing all the time, well, that's looking not good. A blank, total units. Now here we only had one record, but every single record that doesn't have a matching item in the dimension table will get thrown into this row with blank. Now we look at this problem because this does happen sometimes, and when you see that blank, go and look for an unmatched item in the relationship. Now the place that this has happened to me is when I get new data and I forgot to update the date table. Now most of the time my date tables are automatic, but sometimes they're not, and then I get a blank. I have to go fix the date table, and everything is working. Now our next topic in Power Pivot and Power BI DAX is that DAX has no approximate match lookup function like we do in the worksheet with XLOOKUP and VLOOKUP. Now if we look at 36 right here, these are the units. We need to look up the discount. With the lookup function, we take 36, we race through till we bump into the first bigger one. We know it's this row, so we get the discount and bring it back. Now the actual algorithm works a little bit differently and is very fast, but we don't have either of those options in DAX. So here's what we're going to do. We're going to invent some logic. And I'm actually going to show you the logic over here in the Excel worksheet because I can visualize it here much better than over in DAX. And then we'll jump over to DAX and build our formula. Now we're going to use the filter function, and we're also going to use the filter function in DAX. The array, well, I'm trying to get discount, so I'm going to try and filter that, comma, to include, well, here's the units column. And I'm going to ask the question, how many of you are less than or equal to 36? That is virtually the exact formula we'll use over in DAX, but we'll actually use it in the filter argument of calculate. So we get two values, and what we want is the max. So in the Excel worksheet, we can wrap max around filter. Close parentheses. In this case, we can copy it up and down. Now let's jump over and do it in DAX. All right, in the F sales table, we're going to create a calculated column, and we're going to get the max of the disconnected, and we want discount, close parentheses. This is an aggregate formula, so when I enter it, I get the same value. That's the last discount. But how do we change the filter context? Calculate. There's the expression, comma, and now we use filter, and we're going to filter the disconnected discount table, comma, and it is the disconnected units that we want to compare, less than or equal to, and I'm in Power Pivot, so I can click on the units column. Over in Power BI Desktop, you have to type that out. And of course, that will come into the formula through row context. Close parentheses. And now filter will deliver a valid table with the correct filtered rows. Calculate will use that to change the filter context. And max will get the max discount in the filtered column. So when I hit enter, there it is. That is our approximate match lookup formula in DAX. By the way, the logic that we used for this DAX formula was the same logic we used when we did an approximate match lookup formula in M code. However, if you ever have a choice between doing this kind of approximate match lookup in M code or DAX, choose DAX because the DAX formula calculates a lot more quickly. Now, when we have an approximate match lookup table like this, it's almost always sorted smallest to biggest. If you run into a case where the first column is smallest to biggest, but the discount or whatever it is here is not sorted smallest to biggest, we have an alternative. Now, we can use exactly the same formula, but instead of max discount, we're going to get max units. What this does is it brings the matching units from the lookup table over into the fact table. And then we can simply create a relationship. An alternative, since this formula is actually looking up the matching units, notice I used the word match, we can use the lookup value function, which does exact match lookup. Now, the result column, we are trying to get discount, comma. The search column is going to be units because, comma, Control V, that's the value we can use as an exact match lookup. Close parentheses and enter. And that formula will deliver the approximate match lookup without having a relationship. And the difference is these two only require the first column of the lookup table to be sorted. This formula here, which is the much more common formula, requires that both are sorted from smallest to biggest. Now, our last two main examples in this video are going to be table formulas. Now I want to open DAX date table examples. Now, back in video number 4 in this class, we already created date tables using DAX. And this is one of the formulas we created back in that video. Now, generate will do a cross join between two tables. And what we've done is we used calendar, and it requires start and end date. And we use date, year, min, and so on to create a dynamic date. So whatever dates come into the fact table, this date table will always have the correct start to end dates. That's the first table. It's just a single column. Then row creates a single row. Here's the name of the column. Here's the formula. We have the first column, month number. There's the formula. Then month, there's the formula for the 3-letter abbreviation, year, and end of month. This is a horizontal table, and that horizontal table is matched up with each row. And this is the result. Here's another example. We did the same formula, but as a variable. Then we did return, and here we do generate and row. For generate, we use this variable up here. That's the date column. And we actually created variables all the way down for each one of the new columns that we're going to create with the row function, including fiscal year, where April 1 is the first day of the fiscal period. And then we return. Notice we have var return. And then inside of generate, we have more var and another return. So we return, and this is row, creating from all these variables the one row table that gets matched up with this column of dates. You can try either one of these in this DAX file. All right, we saved the craziest DAX trick for last. Here in Excel, and this is going to be an Excel-only DAX trick, here in Excel we have 2 million rows in the data model. But what if we want to extract some of that data into the worksheet? Now, I'm surprised. Power Pivot has been around for about 14 years, and I'm always surprised how many people actually want to do this. And it's crazy because it's not obvious how to do it, and it's a little bit wacky. The way we do this is we go to Data, Get and Transform, and click Existing Connections. Now we go to Tables, and we have Data Model. We're connecting through queries. If you load using the Add to Data Model directly, it'll say Data Model and be that table. But these are what's in the data model. And the key is you want to pick the smallest table, because here's the crazy thing. We're not going to actually write the DAX code to get what we want until we first just connect to one of the tables in the data model. So I'm going to pick sales rep because that's the smallest. So I'm going to double click. And look at this. This is the same import data dialog box we get when we use Power Query. I'm going to put it in B2, click OK. Once we connect to this query in the data model, then a new right-click option appears. I'm going to right-click, go down to Table, and there it is, Edit DAX. If you have a regular Excel table, you will not see Edit DAX. It'll be grayed out. But because this is connected to the data model through Power Query, we're going to click Edit DAX. In the Edit DAX dialog box, the command type is DAX. It says expression. This is where we write our table DAX query. Now, we could write it here, but it's just flat out too hard. It's better to open DAX Studio and type out the formula there, test it to see if it works, and then copy and paste, and we'll paste it over here. So we're going to cancel, go up to Add-ins, click DAX Studio. We'll connect to Power Pivot, connect. Now our goal is to extract the quad records from the F sales table and calculate gross profit for every row. Now it all starts with evaluate, Shift Enter, and we want to filter the fact table. And we could use filter, but remember filter iterates, and that would be 2 million rows iterating. So the table function to use is calculate table. Calculate table will allow us to filter a table, look at any column in the data model for filtering, and it will use the underlying filter mechanism that is much faster than iterating. So we'll say F sales, that's in the first argument, comma, and we can, from our tables over here, if we find the one we want, products, I'm going to double click, equals, and we want quad, and double quotes, close on calculate. Now we could evaluate just this. Let's highlight everything and click Run. And down on the Results tab, we can see the result. Now we want to add a column to this and calculate gross profit. Enter. We're going to use a function called Add Columns. This is an iterator, so it will be allowed to iterate over every row and calculate some formula. In the first argument, we have Calculate Table, comma, Shift Enter. And just like rows, we get to add a column name and a formula. Call it gross profit, comma. Now our formula, we're going to be iterating over this table, and add columns will provide row context. So we can say, actually from our table here, I can just double click line sales. So I'm going to double click minus cost of goods sold. Close parentheses. And now if we evaluate by clicking Run, there's the result. Now we can copy this over here in Excel, right-click Table, Edit DAX. We'll select DAX, highlight, Control-V, and now when I click OK, we're creating a query to extract data from the data model. And bam, there it is with the column we added. Now I created a second evaluate statement that we're going to use over in Excel. But this time I used select columns instead of add columns. The difference is add columns takes a table, keeps all the columns in that table, and adds a column. Select columns, it has a table that you're allowed to iterate over, but it doesn't by itself deliver any columns. You have to say what columns you want. Product, where we're looking up, and because F sales has a relationship between product ID and product ID in the products table, it'll look up the correct product. And gross profit, it'll calculate. And our condition inside of calculate table is I only want units greater than 225. So when I evaluate by clicking run, there's the result. We can copy this. This time I connected to the products table. And we'll go down to Table, Edit DAX, make sure it's DAX, and paste our code, click OK. And sure enough, we extracted the data from the data model. Now, following up on existing connections in Excel and DAX Studio, where we build evaluate queries, this is your bonus section. In Power BI Desktop, of course, we have report, table, model, but now we have DAX Query View. We can build evaluate queries here to test formulas and extract data and look at it. Now on page 52 in our PDF notes, DAX Query View and Power BI Desktop, these are the keywords that we use to define queries. We've been using evaluate, but order by lets you sort. Start at lets you start at a particular place in the sort. And then you can define measures, variables, tables, and columns. We'll see examples of most of these. Now we can build our evaluate query here and click run, and then we see the results down here. Now if you save this, the query up here is saved, but not the view of the results. Now we want to define, and I see it there, enter. We'll define two things, a measure and a variable. I see measure, tab, F sales, that's the table we have to list. And then the new measure we're going to create, even though we have lots of total sales in this model already, total sales. And then we'll do our equal sign and SUMX. All right, so I've defined a measure, and that measure will see the filter context in whatever evaluate statement we create. But I want to create percent of total sales. So instead of a measure, I'm going to define a variable, VAR. We'll call it GT sales for grand total sales equal, and I'm going to refer to the measure I just created. Now, all the other measures besides this one are from the model, which of course I am allowed to access. Now, the cool thing here is that VAR will calculate outside the evaluate statement, and it will only calculate one time and store the grand total in memory. All right, below our define, there's our evaluate, select columns. There's the table, name of the column, name of the new column, and here's where we'll make our calculation. Divide. I'm going to use the measure that I just created above. Total sales, that'll see the filter context in each row and get total sales by product, comma, and then we'll use our variable, which took the measure but calculated it outside of the evaluate. So that'll be the grand total. Close. And when we click run, there's our preview. Now let's see if we can sort. Enter. We'll do order by product. That's the field we just defined right there. Close square bracket. Click run. There we've sorted by default A to Z. If you wanted descending, you would put descending. Enter. And let's start at, we'll start right there, Eagle. And now when I click run, There's our finished table. Now we could copy this and paste it into the data model or over in Excel. Now here's a situation where we're using evaluate across D product. And I pulled a measure that we already created. But this is an alternative. And I just want to check and see if I get the same thing in each row. So I'm going to click Run. And sure enough, I do. Also over here in Query View, here's a measure. And I didn't format it correctly. So I'm simply going to click Format Query to make it easier to read. Now, I got to show you another amazing thing about Query View. I'm going to come over to percent of filtered total. And that's a measure we already created. It has a number of sub formulas inside of it. But watch this. You can right click, Quick Query. Evaluate is not so helpful. Define and evaluate, well, that's OK. But this is the one that is so cool. It'll define each of the sub formulas and then evaluate it using a reference. So I'm going to click this. Here it is. It shows me each one of the sub measures. There's total sales, filtered grand total, and percent of filtered grand total. And then it uses summarized columns to evaluate. And there's the preview at the bottom. Another great option, right-click Quick Queries to find all measures in this model. Now, we used Report View to check each one of the measures. But watch this, define all measures. And this is huge. You can see this preview over here. But it defined each one of the measures, every single one in this model. And then at the bottom, it evaluates. And there are the unfiltered grand totals for each measure. All right, so this is a cool new feature, DAX Query View. Well, that's it for perhaps the most epic video ever created about DAX. It's your one-stop shopping for everything DAX. We talked about the basics like row context, filter context, how they work together. We talked about the powerful calculate function to change the filter context. We talked about Boolean filters, functions to filters, the overwrite operator, KEEPFILTERS to force an and logical test, and perhaps one of the most important topics, context transition. We talked about grain, types of averages, cardinality, and all sorts of other topics, ending with extracting data to the worksheet and DAX query in Power BI Desktop. All right, we'll see you next Dame video.